Alright guys, let's get started on video 1.4.3. This is the last part of our 1.4 notes, and we are going to be describing some processes here. Okay, for each of the following processes, draw the particulate diagram of the reaction mixture before and after the process, and provide a brief explanation for what's happening in each one. So here, for A, we're going to look at H2O liquid going to H2O gas. So I'm going to draw the first one for you, and then in the future we'll pause and you can try it. But this is kind of what we're looking for here. So before the process, your liquids are going to be kind of close together. Not in a perfect lattice because they're not a solid, but they're pretty close together. And that's when they're in the liquid phase. Then afterwards, they're in the gas phase. So you should be drawing them a little bit farther apart. And really here, you can even draw these H2O molecules with little tails moving in random directions. Show them moving all around. Okay, so what's the explanation of what's happening here? So we can say that the attractions between the molecules here, the attractions between the H2O and H2O, in the liquid, they're broken to form the gas. But overall, the substance still remains water molecules. So you still have H2Os, you still have whole H2Os. You don't have H's and O's separate. Okay, so please pause the video and try drawing part B. So you're starting with H2O liquid, so you can draw it just like here. And now notice you're going to H2 and O2 gas. And don't ignore the coefficients there. Alright, so you should have drawn something that looks similar to this. So we started with our H2O liquid, looks the same as before. But in this case, what we end up with are gas particles, and again, you can draw these tails if you like. We have these gas particles, and we have H's and O's separate now. So now we don't just have intermolecular forces breaking, we have covalent bonds breaking apart. So for our explanation, we can say covalent bonds are broken and formed as liquid water is changed to H2 and O2 gases. It's important to say that those are covalent bonds because those are two nonmetals there and that they're not ionic. Okay, go ahead and pause the video and go ahead and try letter C. So letter C is interesting because we have two aqueous phases. So we're going to have our sodium chloride on one side of the dotted line here, so our sodium chloride, and we're going to have our silver nitrate on the other side. Both of these are soluble, so they're both aqueous. So we can see that our our sodium ions and our chloride ions, those are separate, and of course those are going to be surrounded by water molecules in aqueous solution. And the same thing is true of our silver nitrate. The silvers and the nitrates are dissociated from one another. And then after this process happens, we can see that we have formed sodium nitrate, and that's aqueous. So we're going to represent that by drawing the sodium nitrate separate because it's aqueous. However, we did make this precipitate, the silver chloride, solid. So I'm going to show that as a solid here, kind of clumped together at the bottom, our silver chloride. What kind of reaction is this? So this is a double replacement reaction, and one, you're forming a precipitate. So for our explanation, you can just simply say ions recombine to form the precipitate AgCl, silver chloride. So in this one, you can see where that net ionic reaction, or the net ionic comes from. You would cancel out these sodiums and these nitrates because they still stay in solution. And really you'd have the silver and the chloride going to silver chloride. Okay, so like before, go ahead and pause and try letter D. So letter D should look something like this. So we have our aluminum solid. So our aluminum solid, I'm drawing as aluminum at the bottom there. And we have our copper ions are aqueous, so they're up here in solution. Again, I'm not showing the water here, but the water is implied. So what happens is these electrons get transferred in a redox reaction, and we're going to be forming our copper solid. So our copper solid along the bottom here, and our aluminum ions that are aqueous in solution. So for your explanation, you can say the electrons are transferred from aluminum to copper 2 plus ions, resulting in forming solid copper and dissolving aluminum 3 plus. So what we mean by dissolving now is that these solid molecule, or these solid atoms, now become aqueous. So that's the process of dissolving. Okay, go ahead and pause the video and try reaction E. So reaction E, you're going from sodium chloride solid to sodium chloride aqueous. So basically, this is dissolving table salt. So this is what that looks like. You have your sodium chloride. This is an ionic solid. So because it's an ionic solid, you're going to show it in this lattice. So Na plus, Cl minus, Na plus, Cl minus, alternating positive, negative. And this lattice is really, really strong. When you add water in here, it starts breaking apart the chloride and the sodium. So all your waters are surrounding the chloride, and then they eventually pull the chloride off. And then they surround the sodium, and then they pull the sodium off. So really, in solution over here, you can imagine these sodiums and these chlorides all totally surrounded by water molecules. So the lattice of the sodium and the chloride ions are held by strong ionic bonds in the ionic solid, but they're broken by water molecules as they dissolve. In the next page, you're going to be asked to compare some differences and similarities between the processes. So for number 1, between process A and B here, so A and B, what are the differences in what's observed macroscopically? Macroscopically means just what are the differences in what you can see, like what can we see here in the molecule changes. So I want you to go ahead and pause it and try to see what the differences are, and go ahead and list those. Okay, so hopefully you were able to list that both of these are changing to a gas, but B is changing, it's changing much more because you're breaking covalent bonds. So when you're breaking covalent bonds, you're going to need a whole lot more energy. So both are liquid, changing to gas. But B requires much more energy than A. To break covalent bonds. Also, if we have the same quantity of water, so here I had, let's just say, 6 moles of H2O. So if we break the 6 moles of H2O, we'll notice here that we have 6 moles of H2O still when we just go from liquid to gas. But when we're breaking apart the hydrogen and the oxygen, we have 50% more moles. We have 1, 2, 3, 4, 5, 6, 7, 8, 9 now, 50% more moles. So I'm also going to go ahead and write that. Also, if the same quantity of water is changed, B will produce 50% more moles of gas than A. Okay, next question. What are the molecular differences in the bonds and interactions that are broken and formed? Well, in this case, A is actually breaking intermolecular forces, and in this case, it's breaking hydrogen bonds, because hydrogen bonds hold water together. So A breaks intermolecular forces, so hydrogen bonding here. While B breaks and forms covalent bonds. Describe these as physical or chemical processes and explain. Well, A is going to be a physical process because we're just going from liquid to gas. We're not forming any new substances here. So you started as water, you end as water. However, in B, that's going to be a chemical process because you're starting as water and you're ending as oxygen gas and hydrogen gas with very different properties than water. So because you formed a new substance, or new substances here, this is a chemical process. So A is physical. Chemical substances remain the same. B is chemical. Chemical substances change. So they change. In this case, it again is from H2O to H2 and O2 gas. Okay, so let's take a look at processes C and D. So for C and D, what macroscopic evidence shows that a chemical process is taking place? So here, we're going to look at what are we actually seeing in our beaker? What are we actually seeing in these solutions? Well, in C, we're forming a precipitate. So we took two aqueous solutions and we formed a precipitate here. So if you're actually running this reaction, you should be able to see something form on the bottom of the beaker on the sides. In D, originally you had aluminum in your solution, and aluminum looks silver. So you'll be able to see this silverish solid dissolve, right? And then you'll be able to see this reddish solid kind of appear on the bottom. So you'll see one solid dissolve and another one appear, and they're two different colors. So let's go ahead and summarize that. So our macroscopic evidence, so in C, a precipitate forms. In D, the original silverish solid dissolves. And a new reddish solid forms. Okay. In the before process box, show molecularly how the reaction is taking place. Oh, we're already doing that. We already did that, so we can just say C diagram. Okay, what is the difference between the driving forces of these two processes? So what that means is, what's the difference in what causes this reaction to happen? So the driving force for C, or what's causing C to happen, is the precipitate of the insoluble salt, so the formation of this precipitate of this silver chloride. What's causing D to happen is the exchange of electrons. And so that aluminum is going to it's going to give up its electrons to copper, and that's what's going to cause this reaction to happen. So the driving force for C is a formation of the insoluble salt AgCl, silver chloride. The driving force for D is the exchange of electrons, or redox. Okay, next page. In process E, describe the molecular bonds and interactions that are broken and formed. Okay, so let's take a look at E. So the bonds and forces that are broken and formed. First off, the ionic bonds between the sodium and the chloride ions are broken. So those have to be broken in order for this solid to dissolve, essentially. And then new bonds are being formed, and you won't be able to see those bonds here because we didn't draw the water molecules, but the new associations, new attractions, or hydrogen bonds are being formed between water and these individual sodium and chloride ions. So here, we can say that the ionic bonds between Na plus chloride ions are broken, and new attractions between water and the ions are forming. So in this case, these attractions are H bonds. Well, no, actually not H bonds. Okay, is this a physical or a chemical process, and why? I'd like you to pause this video for a second and think about this and take a guess. Is this physical or chemical, and why do you think so? Alright, so in reality, this process would be considered ambiguous. So if you wrote either one, you could be right. So it's considered ambiguous because bonds are broken here. Because these bonds are broken, this could be considered chemical. However, since no real new substances are changing, we still have sodium and chloride ions here. It's just a state change. So then you could call it a physical process. So it's ambiguous. It's a little bit of both. So the process is considered ambiguous. Because bonds are broken, it can be considered chemical. But because no new substances are formed, it can be considered physical. Okay, so what are our takeaways from this? So what is the difference between a physical and a chemical process? So a physical process, in essence, doesn't really change the chemical substances. So something might melt, it might change state, but the chemical stays what the chemical was. So if you have water, and it was a solid before, and you melt it into a liquid water, it's physical because it's still water. New substances are going to be formed in a chemical process always. So in, again, the example A and B with water, if you took water and you split it into hydrogen and oxygen, those are two new substances, so that would be chemical. So physical processes do not change the chemical substances. While new substances are formed in a chemical process. Okay, what are the molecular driving forces of chemical reactions? So what causes those chemical reactions to happen? So either the formation of a new substance or the exchange of electrons. So kind of like we already saw, it could be forming a precipitate, or it could be exchanging electrons. So chemical reactions can be driven by the formation of a new substance or by the exchange of electrons. Okay guys, that is it for 1.4.3 video. Please write down any questions that you have to bring to class and discuss. Thank you.